Hello friends, in this series of videos I will take you to a deep dive exploration of the foundation of deep learning. In this first video I will explain basic concepts of decision algebra using Boolean algebra or binary logic. I will also explain the transformation of decision problem to a binary logic problem by using artificial neurons as decision function unit with clearly isolating the need for multilayer neural network. This will be essential foundation to understand backpropagation algorithm and other advanced concepts of deep learning in future videos. In this short video, we learn briefly the conceptual analogy between decision equation and Boolean equation. Decision function in a supervised learning problem is a binary output function, and a final classification decision might need a set of subdecisions. Let's understand the concept by first understanding very briefly about Karnoff map, which is also called K-map, Boolean equation, and multilayer artificial neural network. The Boolean equation in this first bullet point is represented as a combination of AND gate and OR gate logic in this diagram. The output of an AND gate is 1. So here is an AND gate. The output is 1 if both inputs are 1, like a multiplication, and the output of an OR gate is 1 if any of the input is 1, like a addition operation, but not exactly, because 1 plus 1 in case of binary is equal to 1, not 2, because the digit 2 does not exist in the binary representation. In the table, the possible values of input A are shown at the top. Uh, that is, if the input A can be 0 or 1, and the possible values of input B are shown in the left, 0 or 1, and the cells formed by the columns and the rows contain the output values of the Boolean equation. Now in the first cell for input A equal to 0 and the input B equal to 0 is 0, because if the input A equal to 0 and the B equal to 0, then the output from all of the AND gates are 0, and when all the output from AND gates are 0, that means that all the inputs of the OR gate is 0, which makes the OR gate to give an output of 0, which means we put a 0 on the cell. Similarly, we can understand the other values on the cells. Now, this is called a Karnoff map or K-map in short, and when the adjacent cells along any row or column has ones, then we can reduce AND gates. So here we can see in the row, when the input B is 1, it doesn't matter what is the value of the input A, the output is going to be 1. And similarly, when the input A is 1, it doesn't matter what's the value of input B, the output is going to be 1. And that actually allows us to remove the AND gates, because we can simply put the inputs directly to the output, because that actually is a OR logic, because if any of the input is 1, then the output is 1. It doesn't matter what the other input is. Now we understand how, using Karnoff map or K-map and Boolean algebra, we can reduce the number of gates required to achieve a circuit, binary logic gate based circuit. Now we will look at a actual classification problem, which is a supervised classification problem, very simple one, two-dimensional input space. And we see here that the target values are represented as false or true, depending on whether the point does not belong to a class A or the point belongs to class A. And the input points are represented as input feature 1 and the input feature 2. And we can see here the first 2 points represented by the first 2 rows has the target value 0. That means they do not belong to class A. And now we see that this is not quite completely binary representation, but we will see, we will get more interesting things as we move forward. So now we go to next slide, where we project those points in a Cartesian space, and we see that all the blue color points which belong to class A can be separated by a line from the red color points which are not member of class A. So this green line which is a straight line can separate this the points whether they belong to class A or not. Now we can decide how to make a decision. So from this picture, we'll make a rule for decision. The rule is that if the point, the input point, is on the side of the line which is the other side where from the origin, that means the side where the origin does not exist, if the point belongs to that side, then the decision output will be 1. If the point is on the side of the line where the origin exists, then the decision output will be 0. So with that understanding, we see what happens when we take the decision outputs and put it in this table. So decision output values are actually same as the desired output target values. So that means the problem is solved based on this line, and this line is actually representation of a neuron or geometrical projection of a neuron, and this is also called an OR logic problem. Any linearly separable problem is a OR logic problem that can be solved using a single decision unit or a single decision line. Now we move to the case of a problem which is not linearly separable. So what happens here? In this problem, we still have a binary classification problem, but we will know how to solve this problem by transforming the problem to a binary representation, and that is the most interesting thing here. In this table, again, the target values are on the last column for class A, and we see that the target values are 0 for the 2 points at the bottom row, and that's the only difference between these two problems. And now we'll see what happens when we project these points on the geometrical space. So here we see that the decision unit 1, the green line, we are not able to separate the points that belong to the class A from the points that do not belong to class A, because on one side we have only the points that belong to class that do not belong to class A, and on the other side we have points that belong to class A and the points that do not belong to class A. And the same situation we see for decision unit 2, only thing is that the sides are reversed. So the problem still cannot be solved using a single decision unit or even using 2 decision unit. But what happens, we will see next, how actually these 2 lines are going to benefit us. So now we see when we take the decision outputs for these points, we place it here in this table. We have the binary representation and we have the target values. And since these values are in binary, we have duplicate values, so we will ignore the duplicate values and will only use just one member of these rows if they have the same values. And with that, we see that in the Karnaugh map, the cell for decision unit 1 value of 0 and the decision unit 2 value of 1, the cell value is 0, but it actually should be don't care because that combination of input does not exist in the table. That means in this specific problem that does not arise. And we have already mentioned that this is an XOR problem. Let me go quickly back. Yeah, this is an XOR logic problem and it will be clear very soon now. We are very close to getting there. Now, here we see that in the K-map, we do not have any adjacent cells with value 1 along any row or column. And if we place 1 for the don't care, so don't care means we can put any value there. Any value means either 0 or 1 according to our requirement, which is better. Now, if we put 1, this problem will become an XOR problem, and we can solve this problem using an XOR logic gate. And XOR logic gate can be implemented in hardware, so it's not really a bad choice. On the other hand, I chose 0 to show how this can also be an AND problem, but in the AND problem, we have to have the decision unit 2 input in the complemented form. So we can see now how the binary representation after the problem is transformed using one layer of decision units or neurons by a binary logic gate. Next, we will analyze the same problem if a decision unit on the space of binary represented points can be applied to solve the problem. And for that, we see that we can place a green color line, which is represented by this equation, y minus x equals v. V is the value between 0 and -1 because it's a y-intercept, and we see the y-intercept here is between 1 and -1 and 0 because we see the measurement for 1 is this much, and this line, when it intersects the y-intercept, it's not going to be that, the measurement will not be that big. Now with that in understood, we can now see what happens for the different values, the input values. And we can see that the problem is now a linearly separable problem. So this is equivalent to a OR logic problem. But by following the same rule for decision output, we can see that the decision output is 1 for the blue point and the decision output is 0 for the red point, and that is perfect because the blue point belongs to class A, and we know that the target value for class A is 1, and the decision output for the red points is 0, and we know that the target value for the points that do not belong to class A is 0. And it is the value is 0, or the decision output is 0 for the red points because these red points are on the same side of the line where the origin also lies. So having solved this problem using another decision unit, we have demonstrated the use of multi-layer neural network to solve a linearly not separable problem. Now another thing to notice is that the rule that we have used for decision output is same as a step function. So here we have step function as an activation function. Now we will look at some observations here. So the observation here is that we have solved simple two-dimensional problems with very few points, and when the problem is not two-dimensional, could be three-dimensional, could be four-dimensional, n-dimensional, and it can have a lot more points spread across a large range. Like the minimum to maximum could be very big, and if we try to squeeze all these points within our computer screen or in a wall, if you have, the points can be so close that visibly it will not be possible to find a line to separate them, and to find the measurement also their distance. For that reason, there is a need for an algebraic method to position the hyperplanes such that a linearly not separable problem can become a linearly separable problem after the transformation by the first layer, or if the problem is already linearly separable, then a line or a hyperplane can be positioned correctly so that the decision problem is solved. Now, to do that, we can use an algorithm something similar to linear regression. But linear regression tries to place a hyperplane for a given set of points such that the hyperplane is closest to the given set of points, and is closest to the most of the points. Now, in case of a decision problem, the hyperplane has to be placed in such a manner that the points from belonging to a class and the points not belonging to a class should be separate or far enough from that hyperplane such that the hyperplanes can transform the problem to a linearly separable problem in the output from the first layer of decision units. And that requires a learning algorithm, and that learning algorithm was first developed by McCulloch-Pitts under the leadership of Rosenblatt in the US Naval Research Academy in 1948. In the next series of video, we'll learn about these learning algorithms leading to the backpropagation algorithm.